Hi again, folks. One of the things that I like to review at the beginning of calculus is the idea of asymptotes. They come up pretty often in calculus, particularly in Unit 1. So I'm going to take you back for just a little review of Algebra 2. Here you have a rational function. Remember, a rational function is a function with a numerator. Here you have a numerator and a denominator. And what happens with those rational functions oftentimes is that we can have asymptotes. So these little dotted lines, the dashed lines, they're called, oops, I don't have a pen. Hang on a sec. Let me grab a pen. And then we'll make it bigger for you. There you go. Those are called, that's still not working. So sorry about that. Get that working. There we go. Those are called asymptotes. Now, hopefully you do remember learning about them in Algebra 2, and you probably discussed them here and there, maybe occasionally in pre-calculus, but I just like to go over them. Remember, asymptotes are an imaginary line, and the graph tends to approach that imaginary line, but it never crosses it. Okay, so you can see what's happening there. And then this piece of the rational graph is approaching both of those asymptotes as well. Okay, so I'll just put they instead of asymptotes again, are imaginary lines that a graph, and this is a key word, this word is going to come up a lot in Unit 1, approaches but does not cross. And the concept of a graph approaching a particular value goes hand in hand with the concept of limits that we're going to be talking about in Unit 1. So if you look at the vertical one, remember vertical lines have an equation, x equals some number. And so if you look at the vertical one here, it's going through x equals 2. So that asymptote is the equation, x equals 2. And the horizontal line has an equation y equals some number. And this one happens to be going through all the y values of 1. So horizontal asymptotes are a y equals equation. Vertical asymptotes are an x equals equation. And we always want to represent them as equations. So I'm not so worried about x and y intercepts because I know you can pick those off a graph and domain and range. But in Algebra 2, we had all those kind of discussions. So one of the things for graphing rational functions is starting out by factoring, and this part in particular for us, finding asymptotes is very important, focusing on the denominator. I'll just leave that there. We are not going to be graphing rational functions in AP Calculus. So we have information here. Let me move that up. We have the domain and the range and the x-intercept and the y-intercept. But here is where it becomes even more important, right here. Vertical asymptotes. How do we find them? Well, it's pretty simple. We look at the denominator, we set it equal to 0, and we solve for x. And the values of x that give you 0 in the denominator are the asymptotes. So if we go back to that previous page and we look at our denominator and we take that x minus 2 and do exactly what we were told, set it equal to 0, and solve for x, add 2 to both sides, isn't that what we got for our asymptote equation just by looking at the graph? And it matches up. And that's, if you did not have this graph, that's how you could get that. And that's a very useful skill when it comes to evaluating limits. Okay, so vertical asymptotes, there's just not a lot to say. It all comes from how do we make the function undefined? Because remember, when 0 is in the denominator, that's where the function is undefined. And that's really important information. Okay. I left in the stuff about domain and range and x-intercepts and y-intercepts. It's good information. It's great for you to refresh your memory about what those things are, but my focus here is strictly on the asymptotes. Okay, now horizontal asymptotes, they're a little bit more complicated when it comes to rational functions. Here we're looking at the degree of the numerator and the degree of the denominator. Okay, so let's talk about what that means first. What is the degree? Well, the degree is the amount or the value of the biggest exponent. And the numerator and the denominator do not have to have the same degree. They can have different degrees. When you have a polynomial, for example, like let's say you had y equals x cubed plus 4. Well, the only exponent that you have there is a 3. So it would be degree 3. But if you look at a rational expression, it's essentially one polynomial divided by another polynomial. So it is possible that your numerator degree and your denominator degree are going to be different. So if you look at this particular example, there is really no exponent right here. But we all know that it's really x to the 1 power. So this has a numerator with degree 1 and a denominator with degree 1. So that's what degree means. And I feel it's really important to explain that because a lot of people forget that. We don't use degree that often. But we are going to use it here. There are 3 rules for horizontal asymptotes, or I should say 3 cases. There's the case where the numerator's degree is smaller or less than the denominator's degree. And if that's the case, the horizontal asymptote is automatically y equals 0. So if you look at this case here, we have an x to the 1. And on the denominator, we have an x squared. So the numerator's degree is 1. The denominator's degree is 2. So the numerator's degree is smaller or less than. So this is an example of a horizontal asymptote, y equals 0, which, by the way, is the x-axis. Same thing here. Here, your highest or your largest exponent is 2. Here, it's 3. So the degree of the numerator is smaller than the degree of the denominator. Same thing, horizontal asymptote, y equals 0. Easy peasy. Now I'm going to flip over to the third case for just a minute. This is where it's the flip of that, where the numerator's degree is bigger or greater than. Then there is no horizontal asymptote. So if the numerator's degree has a bigger number than the denominators, you have none. There is no asymptote. So here you have a degree of 2. Here you have a degree of 1. 2 is bigger than 1. So you have no horizontal asymptote. Same thing here. Degree of 5. Degree of 2. Numerator's degree bigger than the denominator's degree. So no horizontal asymptote. So we've covered the 2 cases. What if the numerator is bigger? What if the numerator is smaller? But what happens if they're equal? If they have the same degree? This is the interesting part. Then what we do is we take the leading coefficients of that term. That means we take the coefficient of the term with the biggest exponent. So here, in this particular case, x to the 1, x to the 1, we can see that they have the same degree. Well, if we look at the coefficient, they're just x terms, right? So their coefficient is a 1. We take those two values and we divide them. 1 divided by 1 equals 1. So y equals 1 is our horizontal asymptote. And if you take just a moment and go back and look at our example here, this is the same situation. The leading coefficient and the leading coefficient are both 1. And isn't that what we found our horizontal asymptote to be? Yes, it is. Y equals 1. It is not a surprise. We could now have figured out that information without having that graph. Very powerful. Now let's look at another example here. They're not always going to be 1. In this case, you have a degree of 2 and a degree of 2. So we want to look at the leading coefficients. Here we have a leading coefficient of 4. Here we have a leading coefficient of 2. And we can obviously divide that out and get 2. So our horizontal asymptote is y equals 2. And that would be a horizontal line through 2. So those are your 3 cases. Now what I'm going to do is get you to pause me for just a minute. I want you to take a look at each of these 3 cases. And then I want you to come back to the video and see how you did. I'm going to work through them. So I'm going to shush for just a minute. I want you to pause the video and then come back and check your work. Okay, so coming back, we have 3 examples here. We have the first one. We can do the horizontal asymptote first. We have an x to the 1 in the numerator and an x squared in the denominator. So this is case, I guess if you want to call it case 1, this is where the numerator's degree is less than the denominator's. So the horizontal asymptote is y equals 0. Now, how do we find the vertical asymptote? Well, we take that denominator and we set it equal to 0. Now, you might be thinking, okay, I'm not solving that as easily as what you did before, Miss Lucas. And that's true. We have to do some factoring. So we're going to take factors of -3 that add up to 2. I'm sorry, add up to -2. So hopefully that's going to work out. That'll be an x squared plus x minus 3x minus 3. There we go. And so when we take each one of these pieces and set them equal to 0, we're going to actually get 2 vertical asymptotes at x equals 3 and at x equals -1. So it's possible to have multiple vertical asymptotes. In fact, what I'm going to do right now is pull up my Desmos calculator. Sorry about that. I'll just show it to you. It's just a plain X. Okie doke. I tend to not remember them when I go from screen to screen. I don't know why that is. All right, so there's your equation, and there is your graph. And you can see the vertical asymptote there at 3. Hopefully you can, you can't see it, but you can see the behavior of the graph. It's approaching 3 and approaching 3. Let me get rid of that keyboard. And then here, the same thing. I could draw myself a little line. X equals -1. And then let's see here. Here is the horizontal asymptote, y equals 0. It's not working for this piece, but it's working for these two pieces. So just an example to show you. All right, let's check the next one. The next one, we have a degree of 3 and a degree of 2. So that's this third case where the numerator's degree is greater than the denominator's. So there's no horizontal asymptote at all. But again, vertical asymptote. A couple of different ways to solve this. You could factor it using a difference of perfect squares. That's usually my preferred method. And so you're going to have x equals 1 and -1. And if I put that into the Desmos calculator, I'll show you what that looks like. Just like to give you the visual here, because it really does help to have us see that in reinforcing those asymptotes. Okay, so this looks really funky. Let's make sure that I plugged it in right. X cubed plus 5, x squared minus 1. Yes, I did. But what I'm going to do... Yeah, see, there's pieces here we're not seeing completely. Let's do that. So you can see the 1, the vertical asymptote, and you can see the -1, the vertical asymptote. Clearly, no horizontal asymptote. In fact, this one might actually have what we call an oblique asymptote. Yes, it does, because the degree is off by 1. 1's cubed, 1's squared. This has an oblique asymptote, or what we call a slant asymptote. We don't use those a lot in AP Calculus. I'm not even sure if you covered them in Algebra 2. But they do come up. But I just wanted you to see there is one going. It's looking like the line y equals x is the oblique. And then one more practice one. Let's take a look at that. Oh, good times. Okay, so as far as horizontal asymptotes go, you have a degree of 2 and a degree of 2. So remember, that's the second case where the degrees are equal. So we take the leading coefficient of the numerator divided by the leading coefficient of the denominator. So that's going to be our 2 divided by 3. And there's our horizontal asymptote. Now, this vertical asymptote, you guys might be wondering, is this more of an exercise on asymptotes or factoring? But factoring does come up quite a bit. And this is sort of my public service announcement at this point. If you are struggling with the factoring that I'm doing in this video, please send me an email. Let me know. That way I can give you some, quick help on the side. Even if I'm not in the building, I can give you some help and we can get you, kind of brushed up on that. So with this, when the leading coefficient is not 1, we have to use the A times C method. So we take 3 times -12, which is -36, and we find factors of -36. And we want those factors to add up to -5. So if you think of 36, let's just forget the negative for a minute. You're going to have 1 and 36, 2 and 18, obviously 3 and 12, 4 and 9, and 6 and 6. And I think that's where it ends. But that's okay, because that 9 and that 4, depending on which one's negative, which one's positive, can give us this -5. So I would imagine that the 9 would need to be negative, so that when we added those together, we would get -5. So how do I factor that? I'm going to extend myself down some room here. So what I do is I use grouping. I take the first term and the last term, and I get rid of the middle term as negative 5x, but I replace it with those two factors. The 4 gets an x, the negative 9 gets an x. Now, why did I do that? Well, I want to be able to factor by grouping. So I need 4 things. I need to be able to group into groups of 2 in order to do that. So I'm going to group the first group the second group, and out of each group, I'm going to take out a greatest common factor. Well, 3 and 4 don't have any factors in common. The only thing that I can take out here is an x. Now, 9 and 12, hopefully that's ringing a bell in your head. Those are multiples of 3 and 4. But remember, when this is a negative, we need to take out a negative. And I think we need to take out a 3. So that'll be a 3x plus 4. And the goal is to get this binomial to match this binomial. That way we can factor it out. And then the x minus 3 come together to form the other factor. So those are our factors. And if we set each of them equal to 0, sorry about that, we're going to get negative 4/3 and positive 3. So those are our vertical asymptotes. And of course, we could put that in Decimus if we want, but I think I've kind of beaten you to death on that. But you're more than welcome to use any calculator for that, just to kind of check them out, see how you did, see if you like what you did. And I think that's helpful to have that visual. Now, what you are going to do, we're going to take a look at these problems. I'm going to work these in a separate video. But what I want you to do, this video is going to end here in just a moment once I give you directions. What I'd like you to do is to find all the asymptotes. Now, by that, what I mean are vertical asymptotes and horizontal asymptotes. I did mention the oblique or the slant asymptotes. Not interested in those. So don't worry about those. If they're there, I'm not freaking out about them. The other thing that I want you to notice is the way that they wrote f of x. It's kind of weird. But these are just f of x. They just wrote the x as a subscript, and I'm not sure why. You can just kind of ignore that oddity there. These are just equations. So what you should have is, even if there's no horizontal asymptote or no vertical asymptote, you should be writing none in those cases. That way, in your brain, you will know what you got. And then what you're going to do is you're going to come back to the second video and you're going to check your answers. Okay? So I'm going to end this video here. I'm actually going to let you take a look. There's the first 6 questions. Then you can pause this video, write them down, and then I'm going to scroll down to the last 3. There's only 3 down here. And then you can copy those down, pause the video, and then you can just do these on your own piece of paper. Okay? The one thing I do not want you doing is putting these into the calculator immediately and getting the asymptotes from the calculator. Need to do this without the calculator. If you want to check them, that's great. But in the AP curriculum, you are expected to be able to do that without using a calculator. Okay? And then you will have a second little short video just to show you the answers. Thank you so much.